Well, howdy everyone. I'm Jay. I'm in Massachusetts. It's 1 in the afternoon for me over here, and two of my kids are out getting their second dose of their vaccine. But if any of the other kids bang on the door, you may hear some vibrations from over the different place. But hopefully we'll be able to have a good time. I'm very interested in questions as we go. No need to wait until the end for my sake. And what I wanted to do is kind of give you a sketch about what we're going to do this afternoon, and then we'll get into the actual details. The first thing is I'd like to spend a little bit of time talking about what the vision that I have for blockchain is, to help kind of set the stage for talking about the details of actually developing on Algorand, and to help you understand where Reach fits in to the larger blockchain ecosystem. And I'm afraid that some of this content will maybe be a little bit boring and a little bit duplicative, given stuff that you already know. But I think that it's useful for me, at least, to get myself in the right mindset before I start talking. And then I want to give you kind of a hands-on walkthrough of what it's like to use Reach to develop on Algorand. So that's sort of the spec of what we're going to do. And so let's get started. Now, to start off with, I want to just define a little bit what I mean by developing on Algorand, and what perspective on blockchain I have. Which is that, if I talk to kind of like a random person on the street and I say, oh, tell me about blockchain, they are probably only going to talk about cryptocurrencies, because all they know about is that, wow, there are these crazy cryptocurrencies that, here, let me move this around. We're not blocking. There we go. That should be good. The spectacle of cryptocurrency prices rising and falling and creating this huge speculative action happening out there in the world is very exciting to people. But I think that if that's all you think blockchain is, you're missing a lot of what is particularly exciting about it. So I'm going to kind of ignore the cryptocurrency perspective. And of course, Algorand is a cryptocurrency, but it's so much more than that because of the smart contract features. Now, to help set the stage for what blockchain is really useful for beyond the cryptocurrency, and what kind of decentralized applications you might like to build using Reach and using Algorand, I want to start with sort of two example programs from kind of the conventional world of building, web applications. And so this right here is like a network architecture for a standard website, a standard client-server program that has to make payments. So one component right here is the front end. This is like your web browser. Then there's the back end. That's like the website. And then there's the payment processor. So the payment processor could be a company like PayPal or Stripe, or it could be something that actually is like a credit card processor where you can send credit card information to it. And then there's, of course, your bank. And if, this is kind of from the perspective of a single user, but payment processors are actually connected to many, many different banks. All right, so that's what each one of these things are. Now let's think about the way that these are connected and how the workflow happens. So your front end is going to request to the back end something like, I really want to buy this pair of shoes for $10. Well, at that point, the back end has to get you to give it access to those $10. And there's a few different ways that could happen. Kind of like the old style way is for the payment processor to directly consume the credit card information from the back end. So the front end will say, hey, I want those shoes for $10. The back end says, okay, give me your credit card. Then it takes the credit card, sends it to the payment processor, and then the payment processor gets the funds from the bank and tells the back end, all right, we've got the money. Now, of course, this is risky because the back end, you're trusting it with your credit card information. And it is in fact the case that backends websites have failed to protect their users' credit card information. And so we generally don't trust applications anymore that specifically request our credit cards. Instead, we use other things like PayPal, Stripe, Google Pay, Apple Pay, etc., where what these things do is that the back end says to the payment processor, you better go talk to that front end and get them to give me $10. So then the payment processor will talk to the front end, and this is why there's like a separate window that pops up when you use PayPal that says, all right, you need to pay $10. And then the $10 will go, well, the approval will go to the payment processor, which has the credit card on file, and then it will go to the bank. The payment processor then says to the backend, all right, they paid, and we'll go from there. Now, these payment processors have a reputation of being more reliable than the credit card, than the backend with your credit card information, because they basically have more at stake. So, coolshoes.com doesn't have as big of a reputation as PayPal does. And so that's one, and maybe they don't have the expertise as well. And so PayPal is supposedly doing a much better job keeping track of your credit card information than coolshoes.com would. But nevertheless, they are simply bigger targets. So if we break into coolshoes.com and get credit card information, it's going to be much less valuable than breaking into PayPal and getting credit card information. So there has not yet been an attack on one of these large payment processors that has been publicly known about, but that doesn't mean it won't happen. Now, this right here is the way that things normally work. And so I've talked kind of about why the backend and the payment processor are in a position of trust and how that is risky for users. But the payment processor is also in their position of trust, is also a position of centralization that allows them to exploit their position to charge rents. Rents, of course, being the technical term for fees in an economic system that someone with market power can charge. Now, obviously, the payment processor is providing a valuable service, so I'm not saying that they're completely useless, but nevertheless, they can charge more than they would otherwise. And we see this in practice. Every time you go to the gas station, for instance, and you want to use your credit card to buy, I don't know, some like a candy bar or something like that, and there'll be some sign that says, "Oh, credit card purchases $5 or more." And what's going on there is that the back end is pushing the cost that the payment processor imposes onto its customer, which raises the price of the minimum transaction, which makes it so that there are transactions that we want to happen, you buying the pack of gum, that won't, because the payment processor's fees make it not profitable for you to do so. So with an infrastructure like this, we have risk, we have centralization, which is dangerous, and we have an increased transaction cost, which makes it so that there are transactions that never happen. So that means that the people who can't afford to use, hold on, let me just turn that off real fast. So that people who can't afford the minimum transaction fee won't be involved in doing the activity. All right. Now, this is just taking a payment perspective, but of course, there's another thing that applications do, which is that they also typically will manage data. So let's look at another kind of standard network architecture. Here we could have a front end, that's your web browser. The back end, that's like a website, like a Facebook or a Twitter, etc. And then there's some backend database that's going to be storing information. Now, this is the typical way that things work, where the front end does something, like you press the like button. The backend then says, okay, I'm going to go store the fact that this like happened in the database. And I notice that there's no connection between the front end to the database. So the front end cannot observe the database directly. This means that the backend can store information about its users that is not publicly, that's not available to them to track what is known about them, and that the users do not own their data. Instead, the backend owns the data because it is the only one with access to the database. And this allows them to censor their users and basically lie about the contents of the database. Now, we have in fact observed backend providers using this authority that they have over the database in ways that their users don't like. We observe censoring in the real world. We observe people tracking things that we don't want them to track, among other things. And this only happens because the database is not available to the front end. Now, all of these things are things that can be resolved by a blockchain decentralized application, because blockchains have an infrastructure that looks more like this, where clients, that is what is like the front end, and servers, that's like the back end, they're actually peers in the peer-to-peer blockchain network. And the blockchain network allows them equally to contact the ledger, that is, of course, the accounts, it's kind of like the bank in the first example, or the database. And by exposing this to the world, it means that we can solve some of those issues. We don't have the trust issue because the client can have complete ownership over their account and share only a portion of it with the server without going through any middlemen. This lowers the transaction costs so that more things can clear. And a ledger is just one form of data structure that we can manage with a blockchain. We could manage a different kind of infrastructure like a database. And of course, exposing a real database to the outside world, like imagine that Facebook just expose their SQL database to the world where anyone could log in and do stuff to it. That would be really crazy, because then we could cause havoc and delete stuff that shouldn't be deleted and so on. But the thing that's special about blockchains is that they allow us to manage a data structure with constraints. So for example, the most common constraint that we think about with the ledger is that the total amount of funds in the entire system stays balanced over time. So take Algorand, for instance. There are 10 billion algos, and there will never be a single more algo. And so one of the rules of managing the database is that when you move money from one account to another, the amount leaving one account is equal to the amount going into another account. Not exactly that, because there's also a fee that goes off into this other place. But the point there is that what happens overall is that the ledger, which is a database, allows anyone to modify it, provided the way that they modify it obeys certain invariants. And what building a new decentralized application is all about is essentially determining what data you want to store in this global database and what invariants you want to hold over it. So using the social networking site as an example, we can imagine that the database could store something like, well, this URL has this many likes. And we could allow anyone to do it, but maybe an invariant that we would like is that when you modify the count of how many likes there are, you can only make it go up. And you can only make it go up once. And you can only make it go up by one. And so that would be an example of some constraints that you would like to impose on this publicly managed database. And doing that is what it means to create a smart contract. The smart contract is the thing that lives inside of the database and manages the constraints about what can and cannot happen. And when you think about designing a new decentralized application, you want to think about what your client and server want to do, what their needs are. And then once you understand those needs, then you design a smart contract that actually manages those constraints. Traditionally, when you talk about building a DApp, people focus entirely on building that smart contract up here and saying what the constraints are. Reach is unique. And what we do is we focus on what the client and server want out of the decentralized application, and our compiler automatically produces for users the constraints that the ledger/database will manage. Now, I'm getting a little bit ahead of myself to talk about exactly what Reach is doing, but I just wanted to give you a sense about where we're going. Now, so given that what it means to be a decentralized application is to have one of these smart contracts managing constraints on a data structure, I want to talk about what it looks like to actually do this. The thing is that typically designing smart contracts is an extremely low-level process. What I mean by low-level is that we have a sense that there are languages that are closer to the hardware, like assembly, and then C, and then Python, and then Excel. There's kind of this hierarchy of different languages in terms of how close they are to the hardware. And the closer you get to the hardware, the less things are done for you by your compiler and your language infrastructure, and the more things you have to provide for yourself. For example, JavaScript makes it so that you don't need to worry about memory management. But in C, you do have to worry about memory management. In C, you don't have to worry about where variables live inside of the register set. But when you program in assembly, you have to decide where variables live inside of the register set. So one way to think about what languages do is they provide more services for you as a programmer. Well, typically, blockchain programming is very low level because you have to use languages that provide less for you. And if they provide less for you, that means that you have to do more. And if you are able to do more, then that means that you are a better, definitely a more expensive programmer. And so what this means is that the cost of blockchain development is very high because of this low-level language. Now let's look at like concretely what these low-level languages look like. Essentially what all these low-level languages do is they expose to the programmer the need to construct what's called a state machine. The state machine is essentially a way of writing down the rules for how to manage that data structure that is the blockchain's managing. This state machine, by the way, is like just some really complicated one that I found online. But the key idea is that every single one of these, what this means is that each circle or each node in the graph represents a different configuration of the data structure, and the arrows represent changes that you can make. And the way that you typically have to write a smart contract is that you can't think about the state machine directly, or rather you can think about it directly, but you can't program it directly. Instead, what you have to do is you have to write a different function for each one of the arrows. And the job of each one of these arrow functions is to verify that it really is being called in the state that the arrow is pointing from. Then it will cause the effects to happen and make the changes to the state to move it to the thing that it's pointing to. Let's look at a concrete example of this. So here is an example TEAL program that is out there in the real world. This is something that is for the tiny man automatic market maker. And this is just one little function, the redeem fees function. It goes from here down to return. And when you write in TEAL, which is the Algorand assembly language, you're writing an assembly program. And you have to meticulously know exactly where you're going to store every variable in your program. And your program, by the way, the Algorand virtual machine can only store 256 different variables. And so one of the things that you'll see in this program is it says right here at the top, load 103. And it has a little comment right here that says liquidity _ token _ ID. So the programmer who wrote this, they know that they're storing liquidity token ID in variable 103, but they're not allowed to write load liquidity token ID in their program. They have to remember that it's really that 103. And if we were to study this program, we would look up to the top of the program, and I know from looking at these people's source code that they have a little map there at the top that like says, oh, we use this variable for this number for this thing. And it's kind of funny, they've left blank spots in the memory so that they will like if they ever need more. So like they use like 60, 61, 62, 63, 64, and then they skip down to like 70. In case they ever want something that's near the 60 range. Now this is complicated, and it also turns out to be inefficient too, because it turns out that if you understand the details about how TEAL works, you can actually use way more memory than just 256 if you know about how you can encode things in bytes and stuff like that. But anyways, that's what's going on in this program. So my goal with you looking at this program is to say, this is scary, I don't want to write this. And this is, by the way, it's just one little thing. Now, of course, Algorand also provides something that's called PyTEAL. PyTEAL is very similar to TEAL, but essentially one of the things that it does is it adds a few extra features. So, for example, one of the features that it adds is actually adds the ability to make it so that the mapping from variables to numbers is handled by the PyTEAL compiler. So this allows you to write something like on bid NFT holding dot has value separately from picking the number. But nevertheless, you still have to think meticulously about asserting whether you're in the correct state, then generating the effects, and then making the changes to the global state. And you have to program at a very, very low level with the way that you're thinking about your program. It just so happens that a few things are done for you. So the way that I would characterize TEAL is it's more like a traditional macro assembler, if you've ever done assembly programming, where basic assembly programming requires you to like write down every opcode yourself, but macro assemblers will typically allow you to like generate conditionals and generate variable mappings and just do a little bit extra stuff. And TEAL is really in that macro assembler role. Now, just so you don't feel like I'm like, picking an Algorand or something like this, all other blockchain platforms are just like this. So if we look at a Solidity program, Solidity, by the way, is the most popular programming language for programming Ethereum programs. Ethereum is really the first blockchain platform that allowed people to write smart contracts. Now, if you were to look at like a tutorial about Solidity, you might see a program like this, which doesn't seem very large and scary. And it does have the structure that I mentioned before, where, for instance, right here, it says require. This require is verifying that we're in the appropriate state and the message has the correct form. And then once we do that, we then make the effects. The thing, though, is that this program is not representative of real Solidity programs. Again, if we take a program in the wild, there's actually a program called Uniswap that does the exact same job as Tinyman. And here's an example of a single function in it. So this right here is one function. Now, I have not reformatted this in any way except for removing 3 new lines that were just like blank lines to make it fit on the slide. And this right here, in my opinion, is no more clear than that low-level TEAL assembly code. In particular, one of the things that happens is that when you program in Solidity, you might think that you're using a high-level language like C, where things are done for you. And by the way, I just said a high-level language like C, but many people would not consider C to be a very high-level language. But it's certainly high-level when compared to assembly. But unfortunately, Solidity actually doesn't serve this function of being a high-level language, because one of the things that it fails to do is it fails to actually protect you, the programmer, from having to worry about basically the register allocation problem. Because the Ethereum virtual machine only allows you to refer to stack locations within 16 of where you are, what this turns out to mean is that Solidity basically prevents you from having more than 16 local variables in your program. And if you use more than 16 local variables, then you will get an error that says that the stack is too deep to look at them. And so this is not a theoretical thing that just sometimes matters if you're writing really extreme programs. This shows up in this program, for instance. Right here, it says, this left brace right here says, scope for token 0 and 1, avoid stack too deep errors. What this is saying is that we're going to deliberately introduce a new variable, which is a copy of the token 0 variable, because we know that if we didn't do this, we would run out of stack locations, and then this program wouldn't be able to run. And so the fact that this is here in a real program in the wild shows us that normal Solidity developers need to worry about these things. And in fact, it's extremely subtle to get right, because if you actually count the variables in this program, there's 1, 2, 3, 4, 5, 6, 7, 8. You'd think that you're safe because the error will say you have too many local variables that has to be less than 16, but you would look at this program and there's actually only 8. Well, the thing is that the compiler is going to introduce more local variables for you that you didn't plan on using. And so it tends to be extremely difficult to get your program right when you're programming in Solidity, because so many of these low-level details are exposed to you. So even though you might feel like you're using a high-level language like C, you actually have to be an expert in using the EVM appropriately if you're going to really write one of these programs. Now, this is all to contrast with what it's like to program in Reach. here's a example reach program. It doesn't do the exact same thing, but this program completely ignores the existence of the smart contract and the blockchain network and focuses entirely on the actual people that are really going to be using this program. In Reach, what you do is you write a program in what we call a direct style. And the direct style says that we're going to ignore the existence of that state machine. It's going to be the compiler's job to figure it out. We want you to say who is involved in this program, what do they know, when do they know it, when do they share that information, and what are the constraints about what they say, and then we'll derive the state machine for that. So this is a program that involves Alice and Bob, A and B. And when we read the program, it says, oh, well, at this point in the program, Alice does this, and then she publishes that information. There's no constraints on it. Bob does something. He pays the network. There's no constraints. And then Alice will do something and publish it. And then we'll share the information with Bob. And then we will transfer some funds to Alice, and then we're done. So this program, it takes sort of a disembodied perspective that says, here's what Alice is doing, here's what Bob's doing. If there were more people, here's what Claire's doing. And then we're going to derive from that what the state machine has to be and how to realize that state machine in actual smart contracts. What this does is it drastically lowers the barrier to entry into blockchain programming because you don't need to worry about all those low-level details. But there's more. The thing is that blockchain programs are not only low-level, they're also extremely complex because they integrate all of the most complicated pieces of computer science. They involve complex cryptography, where you have to learn about like, oh, what's the right hashing algorithm for this particular scenario? Oh, what's the right signature scheme here? They involve concurrency, where you have to consider the interaction, the interleaved interaction of all your many different users and guaranteeing that the state never becomes desynchronized among all the different participants and that you correctly handle interleaving events. Reach is going to deal with all of these things automatically for you. And the main way that it does this is through a technique that we call endpoint projection. I developed this during my PhD, and essentially what it says is that we can take that program, which is written in a direct style, where we have the pieces that Alice does, the pieces that Bob does, and they're all mixed together. What endpoint projection does is it separates these out. And the way that it does it is that every operation in your program, we can consider who is the actor of this. So for instance, Alice sends something. And if Alice sends something, what does this mean that we have to know Bob is going to do? So we call that the dual action. So if Alice sends something, then Bob must receive it. And so we can actually take your direct style program and we can derive from it what Alice does, what Bob does, and what has to happen inside of the smart contract. And although I'm using only 2 examples, really it's kind of 3 because there's Alice, Bob, and the smart contract, Reach allows us to do endpoint projection on an arbitrary number of them. There could be hundreds of different things that we're doing the projection of to pull out what each individual piece does. Similarly, we automatically deal with the concurrency by imposing a discipline on Reach programmers where they have to write things where we can figure out a linearization of all the actions that results in a stable value no matter what. And we make it so that those assumptions are pushed out into the clients, so the clients will locally error if they try to do something that would not be possible in the concurrent execution engine, which is what the blockchain actually provides. Unfortunately, there's another thing that's even worse about blockchain programming, which is that not only is it low level and complex, it's like inherently dangerous because it has automatic complete authority over people's funds and over the database, for instance. So this is the reason why if you make a mistake, then you could lose all of your money. As we see every month, there seems to be another smart contract on a network like Ethereum where people have made a mistake and they've lost millions of dollars. Similarly, there's been situations where people have some sort of hack and they take over control of something and make it so that funds are redirected or the service is shut down because they've made a mistake. Well, the normal way that you deal with this, if you're doing traditional smart contract development, is that you pay a lot of money for verification. Verification either through auditing or by becoming an expert in formal verification tools like theorem provers and SMT solvers and so on. And this is yet another thing that increases the cost of blockchain development. And the way that Reach deals with this is that every time you compile your Reach program, we automatically take your program, turn it into a system of equations that we give to a constraint solver, where if there's a solution to that system of equations, then your program has an error in it. When I say a system of equations, think of like, I don't know, if you've ever taken a linear algebra class, or if you remember solving system of equations in high school math or something like that, where you saw something like, oh, well, x plus y is equal to 15, and y plus z is equal to 18, and x plus z is equal to 20. Solve for x, y, and z. So that's a system of equations, which is a bunch of constraints. And we have a request like try to solve it, and that solution tells us something about what x, y, and z could be. Well, what we do is we take your program, we understand it mathematically, and we turn it into a system of equations where we basically say, if there's a solution to this, then that solution is an attack on this person's program. We check to see if there is a solution, and if there is, we tell them about it, and we present it as an error. And if there isn't, then that means that there's no attack, and the program is fine. I keep emphasizing the idea that blockchain development is expensive because you have to have a programmer who is an expert at low-level programming, an expert at complex programming, an expert at writing these 3 different programs, the smart contract, what Alice does, what Bob does, and someone who can acquire someone to do verification or do verification themselves. You might think to yourself, well, I don't care about it being expensive. What difference does that make? Well, the thing is that it being expensive means that there's not as much opportunity for there to be blockchain developers. Because if the minimum bar of being a blockchain developer is that you have to be an assembly expert, a concurrency expert, a crypto expert, and a verification expert, then that means that you need to do a lot of prior training before you can even get involved. So if we remove those barriers and thus decrease the cost, that decreases the cost to you to become a blockchain developer. That decreased cost has another big advantage, which is it makes it so that more entrepreneurs can hire programmers to get their ideas out the door. So imagine that you have a great idea for a cool new blockchain program, but you only have your personal credit card to get your business off the ground. Well, getting your business off the ground with just your own personal credit card is a completely feasible thing to do if you're building an iOS app or if you're building a website. People do it all the time. It's a standard thing to do. And then once they build a prototype, they can then use that to get to acquire some capital. And the capital constraints that you would ask from a venture capitalist to provide for your new web startup is actually relatively small. And so that's why there are so many of them. In contrast, if you need to hire a programmer who's going to charge you $500,000 a year, if you just have an idea, well, you're not going to be able to pay for that on your personal credit card, and it's going to drastically increase the capitalization that you expect from some sort of fundraiser. So that's going to make a big difference in the number of blockchain programmers that are out there. So we at Reach see our goal as not only helping individual developers realize their own dreams, but making it so that it's more efficient for the entire world to create more blockchain programs. So that's why this expensiveness is so relevant and important for us to worry about. Now, the way that Reach solves this is that Reach provides a programming model where we use JavaScript syntax. So we use the most popular programming language on the planet right now to write your blockchain programs. We have a very high level semantics where you get to think about the individual people running the program, and then we can automatically derive the other pieces. And we can perform automatic verification of everything that you write. And this language is also blockchain agnostic. So when you write your program, you don't have to commit first to deploying it on one particular chain. Now, there are chains that we think are objectively better than other ones. I think that you can probably guess which ones that we might think are really better. But nevertheless, it's important to make sure that you, when you start a new business, are not locked into some particular platform because you want to have diversification of your risk. So if one blockchain fails and you need to use another one, you don't want to have to start from scratch with a completely new set of low-level programming knowledge. Similarly, Reach does not mandate using any particular JavaScript framework for building your front-end application or actually doing deployment, because we exist in the normal ecosystem of JavaScript development, where we're a node package and you can write completely normal node programs when you are working with Reach. The best way to get started with Reach is to visit our documentation and join our Discord. And what I'd like to do now is, I, of course, am happy to answer questions. This is kind of a good midpoint in the talk if there are any questions right now. And then what I want to do is actually give you a preview of what it is like to learn and use Reach. So I'm just going to pause momentarily to answer any questions if there are any.
I do not see any questions in the question queue.
Okay. So what I've done now is I've loaded up the Reach documentation site. It's at docs.reach.sh. And when you go, it'll look like this. And the documentation is right now organized into 5 different pieces. There's the overview, the tutorial, the guide, the workshops, and the reference. The reference is a basic reference manual that goes into laborious detail on all of the different things that go on when you write a blockchain program, and how to use Reach. It's sort of like the details. You go there when you're looking for exactly what the name of a function is and what its third argument does and that kind of thing. The overview essentially tells a similar story to what I've just been talking about, but I think that what you want to do is you want to go into the tutorial. The tutorial walks through building an example program. And the goal of building this example program is not to make you an expert on the low-level details about what it's like to program a blockchain program. Also, the goal is not to make you a cryptocurrency, crypto economy expert. So for instance, many tutorials that are out there will say, all right, let's do a tutorial about NFTs, or let's give a tutorial about making an automatic market maker, or figuring out how to provide liquidity or something like that. These are domain problems of excitement today for the blockchain community. But if you don't already understand what the problems are, it can be very difficult and alienating to try to learn blockchain through a domain that you don't already understand. This is one of the reasons why when people are first learning to program, it's so popular to build basic games, because many people learn how to program when they're young, and young people tend to be very interested in video games, even really simple games. And so they're really intuitive to understand. In contrast, like when I went to school a long time ago and learned about programming, I feel like all of my examples were about accounting and I don't know, like computing insurance claims or something like that. And the idea there is that, oh, well, everyone understands what numbers are, so let's have people use numbers. Well, what we're trying to do with our tutorial on Reach is to choose a domain that people are likely to already understand a little bit, or at least it can be taught very, very quickly, where once we understand that domain, then we can learn about how to use Reach and how to write blockchain programs without getting lost in the details about why the world needs liquidity swapped pools. So the problem that we solve, or that we chose to look at, is playing a game of rock, paper, scissors. Rock, paper, scissors, if you're not familiar, is a game where 2 people secretly choose a hand. The hands are rock, paper, and scissors, and they secretly choose these, and then they reveal them at the same time. And then there's a simple way to determine the winner, which is that rock beats scissors because it smashes it, and then scissors cuts paper and destroys it, and then paper covers rock, which kills it. And so that's the way that the game is played. And it's a simple problem that shows up that is sort of instantaneously familiar. Now, what we do in our tutorial is we take this problem and we build an environment where people can play a game of rock, paper, scissors and have a wager over who will win. So I could bet Russ 5 algos that if I win, then I get his 5 algos. And if he wins, he gets my 5 algos. And if we tie, then we just, get them back. So that's the problem that the tutorial is about. The first part of the tutorial walks you through how to install Reach and get it running. Reach is a Dockerized program, which means that if you have Docker Desktop installed, then you don't need to have any other pieces of software. If you're on a Mac, then you already have tools like Make. Similarly, if you're on Linux, you probably already have these. And if you're on Windows, then you can install WSL. We have a guide for installing Reach on Windows. And then you can install Docker. And Docker will allow you to download the Reach tool, the Reach compiler, without having to worry about exactly what the system dependencies are. You download Reach by running this command right here, and you'll know that it works if you can run Reach version. Now, I'm going to go into the terminal, and I'm going to talk through the things that are the tutorial itself is about. So let's go into a terminal. Let's go over here. All right. So, actually, you know what? Let's go right here. So writing a Reach program looks like this. We write something that is syntactically identical to JavaScript, but it's sort of like JavaScript with some special new functions. So right here we write main is a Reach application, and the body of main is going to define a participant named Alice and a participant named Bob. We then deploy the program, and then we're going to write our program down here. When you write a Reach program, you also write another program in JavaScript, which is going to serve as the actual logic of what Alice and Bob do. And good programming practice is to write a test before you write the real thing. And so I'm going to walk through writing automated tests before writing like a web application. And so this right here is the sort of the structure of typical test programs, where you're going to import the standard library of Reach. You're going to import the compiled version of your Reach program, because when you compile your program, it compiles into a JavaScript artifact. You're going to load the standard library. And then what we're going to do is we're going to create new test accounts that will serve as Alice and Bob. Alice will create the contract. Bob will connect to the contract. And then we'll run the logic for Alice, and we'll run the logic for Bob. Now, these programs don't actually do anything yet because there's nothing there, but this is kind of the structure. And then when we run our program, we will write Reach compile. And Reach compile is going to actually compile our program. Notice that there's a warning that says there's no publications in this. This is not a good program. It will then verify it. And then after it does that, then that will create the compiled form of our program, which I'm going to open up just so you see that it exists, even though you don't actually ever care about it. So right here is the compiled version of this program, which, as we said, doesn't do anything yet. But in here, you can see that it has right there, here's the TEAL program that got generated for this program. And it's very short because the program doesn't do anything. And then we also generate an Ethereum program, which is shown as compiled bytecode. So you don't see the source code for that. All right, that's just kind of the structure of a Reach program. We compiled it, and then we can also run it in a test scenario. And the test scenario is going to start up using Docker an Algorand test network, deploy the program on that Algorand test network, run the example behaviors, and then stop. But of course, the example behaviors don't do anything yet. So we've just walked through the entire structure of writing a Reach program. You write your program in Reach, you write a test in JavaScript, and then you compile and run your program at the command line. And we have an IDE that's part of VS Code that makes it so you don't need to use the command line at all. And you never have to decide or interact with the underlying blockchain network yourself. Everything is abstracted for you. Let's move on and look at something that actually does something. So let's go. Look at an example program. Okay, so this is the second step of the tutorial where we actually make the program do a rock, paper, scissors thing. So here we say that Alice is a participant that obeys the player interface. See, in a reach program, you're only going to specify the structure of the computation. You're not going to specify the details. So for instance, we know that Alice and Bob have to have some way of deciding what hand they want to play, whether rock, paper, or scissors. But we don't want to mandate in the program exactly how they do this. Because of course, probably what's really going to happen is that you're going to present a user interface that's where they're going to click one of them. But if we made it so that the reach program had to show, had to say how to do that user interface, then we basically need to replicate everything that, you know, JavaScript provides for doing React programming or something like that. But we don't want to do that because that would make us that we would have to pick the only one true way to do that. Instead, we take kind of an object-oriented approach where we say, well, there's an interface between Alice, the thing that represents Alice in the decentralized application, and the front end, which is the user experience. And so we say that there's a function called getHand, which is going to return a number, and the number is going to represent what hand we want to be played. Similarly, there's going to be another function that's going to allow the user interface to see who won. So we say that Alice and Bob are both players. Alice is going to start off by choosing her hand, and then she's going to publish that for all the world to see. There's not going to be any constraints. Then Bob is going to publish his hand, or decide and publish his hand. Then we are going to compute the outcome. And then after we compute the outcome, that'll be visible to everyone, and then we're going to share that with the individual users. So let's look at the front end for this, which is a test scenario. So the test scenario looks the same as before. The preamble is exactly the same, but the rest of the program looks different because the rest of the program is going to actually define those functions which we said had to exist. So there's going to be a getHand function that takes no arguments and returns the hand, and we're going to make it so that it chooses randomly. And then the C outcome is going to print a message that says who saw what outcome, and we're going to have these arrays that says that rock is 0, paper is 1, and scissors is 2. Bob wins is 0, a draw is 1, and Alice wins is 2. And then when we run the programs, we're going to say, well, Alice is going to run, and here's going to be the implementation of her player functions, and here's the implementation of Bob's functions. So when we go off and we run this program, if we write reach run, it's going to compile our program and then run it. It's going to say Alice played rock, Bob played scissors, Bob saw the outcome, Alice wins, and Alice saw the outcome, Alice wins. Notice that they both agree on the same outcome. This is because the point of decentralized networks, of blockchain networks, is to for different parties to reach consensus that is agreement over what happened on the network. This is one of the reasons that they're also called consensus networks. Consensus network is the general term for what the technology of blockchain provides. As an analogy, transportation is a goal, and that goal can be provided by cars, trains, bikes, skateboards, horses, carriages, starships, etc. So similarly, consensus networks are the goal, and that's like the actual product. And there are many ways to provide those, blockchains being one particular way to provide them, and the Algorand or Ethereum blockchain in particular being a way to do it. Now, so far, notice that our program, it works, it does something. It doesn't mention anywhere that we're using Algorand or using Ethereum. Behind the scenes, it is using Algorand. And if we wanted to, we could run in a debugging mode, and it will give us lots of information about what's happening behind the scenes. It'll be an extremely large amount of information. So I'll just let it fly by. So here, for instance, we see, the actual like Algorand addresses that are being used. We see the fact that there are like transactions being generated that have certain fields inside of them and what exactly is going on. None of these details are relevant to a normal programmer. They're only used when you have some problem and you need to, probably you probably never need to look at them, but maybe you'll have a problem someday and you'll ask someone on the Discord channel, oh, what's going on here? And I might ask you for the debugging log, and that'll be helpful for me. Okay. This program, of course, though, doesn't fully realize our goal for the rock, paper, scissors because there's no actual wager. So let's do the wager next. So what we've done is we've added something to the program, which is that Alice is going to provide a wager, and Bob is going to have a function where he can accept the wager. Alice is going to not only publish her hand, but she's also going to publish the wager and pay that amount into the contract. Bob will have the opportunity to accept the wager, and if he does, then he'll pay into it. And then we'll compute the outcome, and then based on what the outcome is, we will compute the payouts. If Alice wins, then she'll get 2 of the wagers. If Bob wins, he'll get 2 of the wagers. And if they tie, they'll each get 1, and then we'll transfer the appropriate amount to each one of them. Notice that this program is still very svelte. It's only 46 lines of code. Let's look at the test program. The test program is going to be a little bit more elaborate, where we're going to, before the program runs, get the balances for Alice and Bob. So we can say, oh, I started with $100 and I ended with 96. And then the other thing is that we're going to say that Alice is always going to wager 5 and Bob is always going to accept. And then we're going to get the balances afterwards and say, oh, Alice went from this amount to that amount, and Bob went from this amount to that amount. Let's run the program again with this new version. And we will see that Alice plays paper. Bob accepts the wager of 5. Bob plays paper. There's a draw. And Alice goes from 100 to 99.996. And Bob went from 100 to 99.995. Notice that they lost money even though there was a draw. And the reason they lost money is it costs money to run the smart contract. It costs money to do things on the blockchain. There are fees associated with running things. And Alice pays slightly less in fees. Basically, why does she pay less in fees? Essentially, one of the fees that she pays gets refunded to her. That's why. On Algorand, you pay something to create a smart contract, but then you get that reimbursed to you when you're done with the smart contract. So that's why she ends up with less funds. Another reason is that notice that Bob is going to pay and publish, and there's going to be these 2 transfers, and those 2 transfers are also going to cost something. And the way that it works is that whoever originates the message that makes them happen has to pay for it. So that's why Bob has to pay more, basically. Now, at this point, I want to show you what it's like to not use Algorand, but use Ethereum instead. So I'm going to change this. I'm going to write reach connector mode equals ETH. And this is going to make it so I'm going to run my program on Ethereum instead. There's not already an Ethereum blockchain running. So it's going to say, oh, look, I'm going to create the reach devnet ETH. And so that's going to create the test Ethereum network. And then we run this and notice that, something different happened this time, but also that the amounts are different because the cost to execute transactions is vastly different on different networks. And so that, shows up in these extra decimals. But the only thing that required me to change when I went from one network to another was changing a single environment variable in the infrastructure of the program. I didn't actually have to change I didn't change the reach program, and I didn't change the test program in any way. This is what we mean by reach being blockchain agnostic. Now, the next thing I want to show you is the way that Reach protects you from errors in your program. So imagine that we accidentally made a mistake. This is going to be a really dumb mistake that you wouldn't make in practice, but it's going to represent something that would happen in the real world. Imagine if we thought that when Alice won, she would get 2, but then also Bob would get 1 wager. This is actually impossible to happen because there is only 2 times the wager available for the contract to spend. So it's not possible for Bob to do this. So if we accidentally had this 1 right here, the program would be broken and it would not be possible to run when Alice won. What it would mean is that if you ran this program and Alice in fact won, then this code could never run. And since that code could never run, it would mean that the funds would be locked away forever. So what happens when we try to compile this program? When we try to compile it, it says that during verification, there were 4 failures. It says that on line 40, which is this line right here, when we're trying to pay Bob, it says the balance, we were trying to prove that the balance was sufficient for a transfer. And it says that we formalized this theorem in the following way. You were trying to claim that variable 110 would be true, but actually it would be false. Where 110 is basically saying that this number right here is less than this number. This number is the total balance at the time. And this number is how much we're trying to give Bob. It says that this could happen if Alice bet 1, if Alice returned 0 and Bob returned 2, which makes it so that Alice wins. And if that happens, then the outcome will be that Alice wins, which means that the payouts will be 2 and 1, which means that this theorem will be false and your program can't run. And so we automatically detect situations like this where you try to overspend. It turns out that we also protect if you were to try to underspend. So here I've changed it so that Bob gets 0 and Alice only gets 1 when she wins. So this is also a problem because it means that the funds are locked away in the contract forever. So when we compile this program, it's going to say that there's an error. And the error this time is on line 8. It says balance 0 at the end at application exit. And it says that, well, if Alice wagered 1 and she played 0 and Bob played 2, then that means that she would win and that we would try to spend 1 and 0. But that means that we're going to try to prove that 0 equals this number right here, which is, well, 71 went in and 71 went in again. That's the 2 wagers. And then we took away variable 100, the 0 thing, which is 1 times 71. And then we also took away the other one, which is a 0. And that is equal to 71, not 0. So this is false. So that means that the program leaves money on the table. So this is what we mean by Reach automatically detecting errors in your program. Now, the rest of the tutorial develops this program in a deeper direction. I want to kind of skip ahead a little bit to the last version of the program to give you a sense about where this leads to. RPS 7. Okay. All right. So what we eventually do in this program is, first of all, we build a convenience library for talking about the values rock, paper, scissors. We abstract away the function that computes the winner, and we build some test cases for it where we say, oh, well, when rock and paper are played, that means that B wins. And if paper and rock are played, that means that A wins. We prove a theorem that no matter what hand Alice and Bob choose, the winner is always one of the valid outcomes. And then we also prove the theorem that if you play a hand against itself, it always results in a draw. The theorem prover that Reach uses for its verification allows you, the programmer, to insert your own unique verification claims that are interesting only to your program like the fact that, there should always be a draw when two people play one another, no matter what the hands are. We also extend the program to be more secure by introducing what's called the cryptographic commitment pattern, which requires us to provide randomness. And we also deal with a problem that happens a lot on blockchain programs, which is, what do we do if someone decides that they're not going to play the program anymore? The wager is set with a number. The deadline is set with a number. The deadline is how long people have before they answer their side of the computation. We have Alice publish the wager in the deadline. Then we have Bob accept the wager. And if he doesn't, then Alice gets her money back. And then we're going to enter a loop where in this loop, we're going to keep playing until there is no longer a draw. So we're going to make sure that we keep playing until somebody wins. And in it, how it's going to work is that Alice is going to cryptographically commit to her value, which she does by using the make commitment function, which is something that we don't need to understand the cryptographic details. It's just an interface that Reach provides. And then we're going to make another theorem claim that Alice has secret information that Bob doesn't have access to. He can then choose his hand without knowing what Alice did and then publish it. And then Alice will then reveal what her hand was, and then we will compute what the winner is. And then depending on who the winner is, it was always either Alice or Bob. All the funds will go to either Alice or Bob, and then we'll be done with the program. We also build an interactive version of the front-end program in JavaScript. Rather than having it be a purely automated test scenario, instead what we do is we build a little simple text-based user interface where we say, oh, are you Alice or are you Bob? Do you want to create a test account? What contract are we connecting with? What's your balance? How much do you want to wager? Do you want to accept the wager or not? And this is a really, really simple JavaScript program that just does basic user interface, printing out a question, reading in an answer. And it's not to sort of show off our amazing skill at making beautiful JavaScript user interfaces. It's just to show off the idea that you don't need to use any special Reach or blockchain knowledge. You can use whatever you already know about building JavaScript, and it will just work in Reach. Our Reach program, by the way, is exactly 100 lines. And our interactive program is 106 lines. Let's actually run it and see what it's like. I'm going to run Reach run. It's going to say, am I Alice? Yes, I am Alice. Would I like to create an account? Yes, I would. How much do I want to wager? I want to wager 50 algos. Now it says the contract's deployed as 63. But of course, now I'm just sitting here waiting for Bob to join. So let's make another window. And in this new window, we'll run another instance of the game. This one's going to say, am I Alice? I'm not Alice. I do want to create an account. And it says, please paste the contract info. So I'm going to type in 63. And it says, do I accept the wager of 50? Yes, I do. And it says, oh, what hand will I play over here? So let's go over here and say, I want to play rock. You played rock. What hand will you play? I'll play rock. You played rock. Oh, now it's going to ask me again. It asked me again. Therefore, I know that there was a draw. I'm going to play rock again. Over here, we'll play paper. Now we see the outcome is Bob wins. My balance is 949, and the balance over here is 1049. So Bob won, and he claimed the 50 algos. Again, my program is completely agnostic to what chain it's running on. If I wanted to, I could run my program again, this time using a network like Ethereum. I'm going to run over here, and I'm going to run again over here, reach connector mode equals ETH. I am Alice. I do want to create an account. I want to wager 5. And now I'm not Alice over here. I do want to create an account. Now I have to paste the contract information, which is bigger. Oh, that's annoying. Okay. All right, I think that's right. Oh no. There we go. All right. Do I accept the wager of 5? I do. We'll play rock, and then we'll play paper over here, and then we'll see what happens at the end. So my program doesn't need to change in any way to run on one blockchain or another. Now, these programs are relatively simple. So we've got a 100-line reach program and a 100-line JavaScript program. Now, what would it have taken if we wanted to do this by hand, i.e. not using reach? Well, that means that we would have to produce, let's look at the code that got compiled. So we're going to write, this is what the reach compiler produces for us. So the Alice program goes from line 37 to line 500. So the Alice program ends up being about 460 lines of code. And that's just for the part of Alice that interacts with the blockchain. The Bob part goes from line 501 to 914. So that's again about 420 lines. Now let's look at the TEAL program that got generated. So the TEAL program goes from line 922 to line 2147. So that's like 1,200 lines of TEAL. And if we look at the Solidity program that got generated, that was about 800 lines of code. So the burden of creating even this simple application of 2 people wagering over rock, paper, scissors, continuing to play until one of them wins, is simply enormous when you use a low-level programming language like TEAL or Solidity and have to directly interact with the SDKs provided by the underlying consensus network. But when you use something like Reach, literally thousands of lines of code are written for you, and you don't have to think about any of the complexity of really operating on the blockchain. You can focus entirely on the business logic of what you are interested in, and everything is provided for you. Now, I've only shown you what it's like to make simple test programs and make programs that have text-based user interfaces. But in our tutorial, we walk through building things that use, for example, React to make a web interface. And the web interface is definitely more code, but all of the complexity of that code is because it's hard to write web programs. And I've also only showed you something that does something simple, like a wager over rock, paper, scissors. But all of those examples that people are interested in and passionate about, like NFTs and liquidity swaps and auctions and things like that, those are all possible to do on Reach as well, and many of them have already been written by members of the Reach community. To finalize, I want to remind you that if you are interested in Reach, then I hope that what you do is that you join our Discord and read our documentation. And you'll find many people there on the Discord who are interested in helping you build your cool DApp that you have in mind. And I hope that the documentation will be useful for you to get started. Thanks so much for spending your afternoon with me. And I'm, again, very happy to answer any questions. But you've been a great audience. Thank you.
Thanks, Jay. Great session. I also posted in the Reach Discord on the chat window for people to join. Highly recommend that. Link to the docs and also the session that JP and I did in Tampa a couple weeks ago on Reach. So some additional resources for the folks today.
Awesome.
Sapphire, any closing remarks?
Hey, I'm just going to start sharing my slides. But yes, if anyone has any questions, like Russ and Jay said, please put them into the Q&A or the chat before we close today's session. I am just going to start sharing my screen. Let's see. Let's get the right one. There we go. Jay, if you could stop sharing your screen and I can share mine, that would be great. Thank you. Perfect, thanks. Okay, let's just get to the right slide. Here we go. Okay, I just want to take this opportunity to thank you, Jay, for sharing your knowledge with our community. And this is a fantastic session, which will be published on YouTube soon. So we'll let the community know on Slack when that's going to be available. And it'll be available for all of our members that couldn't attend today as well, as we have our blockchain community at Women Who Code is across the world. And yeah, so like Russ said, he shared some links to the Algorand Discord in the chat for anyone to join them. And yeah, again, thank you, Jay and Algorand, for this wonderful series. You can find our whole series on the YouTube channel for anyone that missed the previous sessions as well. And we are so grateful for your support and sponsorship. Thank you so much for that. And also thank you to our blockchain volunteer, Manageri, who was moderating our chat today as well. So we have an upcoming event, blockchain, just one before the break. It's on December the 18th at 10 AM EST, and it is a meet and greet event with the blockchain community. So it's a lovely chance to connect with the community members, get to make new friends, maybe ask for some advice on careers or blockchain at all. So yeah, it's a good opportunity to meet with people. And yeah, you can follow us on our blockchain social media pages, and you can register events here at womenwhocode.com/blockchain/events. And if you have any questions at all, you can reach out to blockchain@womenwhocode.com. And our social media pages are linked here as well. We have Twitter, Facebook, Instagram, and LinkedIn, where we share and update all the information about our upcoming events and share knowledge with our community as well. So thank you again. Thank you for our speaker, Jay, Russ, for coming along and helping with the questions, and our attendees, and of course our sponsor, Algorand. Thank you so much. I stop sharing my screen. Have we got any more questions coming? No. Okay. So if anyone has any questions for Jay or Algorand or the Russ, please join the Discord and you'll be able to ask some questions in there as well. But yeah, thank you everyone for coming along today. And I hope you all have an awesome day.
Take care. Thank you.
Bye, everyone.
Bye.